one of the examples that John used is that if you take young cells, put them in the old matrix, and that makes those cells behave like old cells. And conversely, if you have old cells, but you put them in the young matrix, then those cells start behaving as young cells. And to me, actually, this is already an interesting observation that basically means that cells can interpret external signals and behave differently, and so we actually can potentially override those signals. So even if we're unable to change the matrix, we can maybe change the cells by partial reprogramming or some other methodology to actually ignore external cues and fool them into they're young, or make them behave as if they're young, upregulate their gene expression of the good stuff, downregulate the bad stuff, basically shift the pattern of their gene expression towards a younger pattern. And this is really the idea behind partial reprogramming, where we take genetic factors and try to convince the cell to shift its gene expression pattern, try to influence the cell to shift its gene expression pattern towards that observed in younger cells. But I think more philosophically, from my perspective, I think aging looks more as if it's actually programmed than completely random, because as I showed in my talk yesterday, if you look at the animal kingdom, there's so much variation in lifespans and speeds of aging that to me, I think that all this variation is caused by randomness, and including the observations that epigenetics can influence even within a single species, greatly influence lifespan. And for example, according to some external cues, can greatly expand lifespan or shorten lifespan. Like my favorite example is the monarch butterfly, that if they're born in the summer, they only live 1 month, but if they're born in the fall and they need to go to Mexico for the winter, they live for 9 months. So obviously there's great modulation of lifespan, and nature has this ability to have much longer lifespan, but sometimes it chooses to shorten the lifespan of the species. And also another observation that to me points to at least a signaling of a programmed nature of aging is the observations that we see with paradosis, where we connect a young individual and an old individual together in the blood circulatory system, and we see that the old individual is rejuvenated while the young individual is actually aged. But then you disconnect them and they return to baseline. And to me, this shows that aging is reversible, at least the aging of that model system. So it's not necessarily just stochastic accumulation of damage, because if you rejuvenated the old organism and you separated it, but then it returns to baseline, then obviously somehow we were able to reverse that damage that potentially we think should be reversible if we think about aging as the stochastic accumulation of non-enzymatic damage to long-lived molecules. And another observation, again, to me that talks against this hypothesis is that if you transplant organs, even young organs, to an old organism, you see very quick aging of these organs. And so it's not necessarily the matrix that ages them, because if you take like a whole heart transplanted into an animal, and you see that heart being aged, obviously the heart came with its whole matrix, but somehow if you put it in the whole organism, it very quickly synchronizes with the age of the organism. And so to me this implies that there's some sort of signaling, systemic signaling that ages that organ, and not necessarily just random damage that is at work there. And so basically all of that preamble means that for me aging is driven by epigenetics, and so if we intervene at the level of epigenetics, not only will we be able to reverse this kind of signaling that tells cells you're old, but even if in the context of the matrix, we could also potentially tell cells to ignore the matrix signaling. So essentially we're getting like the best of both worlds by intervening at the level of gene expression. Then ultimately, of course, cells, they do the work, and they do the work at the level of proteins that are expressed in those cells. And so if we are able to force the cells to ignore external cues, we can potentially rejuvenate it by the approach of some sort of epigenetic modulation, of which partial reprogramming is one such approach. But of course, that said, I welcome trying other approaches as well, including the replacement approach. Oh, but one thing I'm worried about the replacement approach is that if aging is driven by systemic signaling from the brain, and the brain has the control center that actually synchronizes the rest of the tissues, then replacement will not work, because if we transplant the head on a new body, that old head might actually quite quickly age the rest of the body. And so a key proof of concept experiment in this case would be switching heads between an old individual and a young individual, mice, of course, for now. Essentially, it's like heterochronic parabiosis, but actually heterochronic head transplants, and to see would the old head rapidly age the new organism. If that happens, then replacement might not help us. Or, and conversely, would a young head rejuvenate the old organism, and this will be conclusively then telling us that there is this systemic signaling happening in the brain that can either rejuvenate the body or quickly age the body. And this will serve as a convincing experiment showing whether the replacement paradigm is viable or not.